Hello students, welcome back. Let us resume our discussion in section 1. Previously, we went through the relation between the sign of the first derivative and the increasing-decreasing nature of the original function. In short, if the derivative is positive, then the original function is increasing. The graph goes up. If the derivative is negative, then the original function is decreasing. The graph goes down. And here's a visualization for the former. Please note that the derivative or the slope of tangent line is positive. And here is an illustration for the latter. Here, please note that the slope of tangent line, the derivatives, those are all negative. And then, what if the derivative hits 0, or if the derivative does not exist? In that case, we say the graph has the critical point at that x-coordinate value, or the original function f has a critical point at that x-coordinate value, and there are various cases. First two cases are the most important, local minimum and local maximum, and then followed by the next two cases, keeps on increasing, keeps on decreasing. And last two cases are rather singular. Local maximum, in that case, the derivative changes positive to negative, so the graph of the original function goes up, hits the maximum, and comes down. And that's visualized by this diagram as well. And then this case, vice versa, local minimum. The derivative changes from negative to positive, so the original function changes from decreasing to increasing, and that's visualized by the diagram as well. And then in this case, keeps on increasing or keeps on decreasing, even though we have momentary pause here and there. So horizontal tangent, yes, but neither maximum nor minimum. Those kind of points are examples of so-called inflection points. But we're going to discuss the inflection points a bit later in the next subsection. Okay, I guess we are ready to go to the next subsection. Okay, let's go. When the second derivative is positive, or equivalently speaking, first derivative is increasing, the original function is concave up. Look at these three cases. The original function is increasing, and the last case decreasing. Here, increasing and it changes to, the other way around. Decreasing and changes later to increasing. In any case, we call the graph is concave up. Look at the upper part of the graph. Graph is bent upward. Graph is bent upward. The graph is bent upward. See that? In this case, we say the graph is concave up. Original function f is concave up. Now, let's look at this in terms of the first derivative. The slope of the tangent line. Okay, maybe it's going to be better with the drawing mode. Okay, around here we have a tangent line like this. Around here we have a tangent like this. Around here we have a tangent like this. See the difference? Used to be very flat, getting stiffer and stiffer and stiffer. The derivative increases. The slope of tangent line is getting bigger and bigger and bigger. Again here, slope is negative like this. Slope is negative but a little bit less. And then here slope is 0. Now slope is positive now, and even more positive like this. See the difference? The slope is getting bigger and bigger and bigger. The derivative is increasing. Same goes here if you look at various slopes. So concave up is associated to increasing derivative. And then if you take the derivative again, increasing is associated to positive derivative. So derivative of the derivative, the second derivative is positive. So we get this result. Concave up means derivative increases, second derivative is positive. Let's get out of this drawing mode. Okay, now this visualization specializes the middle part, but the first and third part pretty much the same. Pay attention to the slope of the tangent line, and right now it's very negative, and that's visualized by very red. And then as I move to the right, slope changes to, let's see, pretty close to 0 and keeps getting bigger and bigger and bigger. And then here very positive, and that's visualized by blue. Let me run it. See the change? See the change of slope? And see the change of color. Okay? Used to be very negative, but increase, and then becoming positive. So what do you see? The derivative is increasing. That's what I want you to see. The derivative is increasing. The slope gets bigger and bigger and bigger. It used to be very negative, less negative, hits 0, now positive, and even more and more and more positive, like that. We can do something similar to this portion and that portion as well. In any case, here's a summary. Second derivative is positive, or the first derivative is increasing. That means the original function is concave up. So these three are the same. Second derivative is positive, first derivative is increasing, the original function is concave up. Those three are equivalent actually. Excuse me, not really equivalent. There are some counterexamples, really weird examples here, so I cannot say equivalent, more or less the same. Okay, I'll say this like that. Those three are more or less the same. Now, the other version, concave down. Decreasing, in any case, concave down. Derivative is getting smaller, smaller, smaller. And look at the graph downward, concave down, and then concave down, concave down. Graph is bent downward. Second derivative is negative, and the first derivative is decreasing. And then here's an animation associated to that. Oops. See the change? Look at the slope, pay attention to the slope, and that's visualized by color. Very positive, very blue, and then gets flatter, 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 and hits horizontal 0, and then becomes negative, and then gets really negative, getting more and more red. And then one more term. When the concavity changes at some x-coordinate value, we say the graph has the inflection point at that value. Of course, inflection points means the point c comma f of c, but really nobody cares about the y-coordinate. So we say inflection point at x equal to c. I have never seen anybody using the term inflection number or inflection value, just inflection point. Just like the critical point, the point is important, and pay attention to the x-coordinate. Here's an example of an inflection point. Concave up here, concave down here, and a change takes place right here. Another example, concave up here, graph is bent upward. Concave down here, graph is bent downward, and a change takes place here. Another one here, concave up here, and then concave down here, and the change takes place right here. And in this particular case, this is a critical point, horizontal tangent, and then inflection point at the same time. Yes, this kind of thing happens when the graph keeps on decreasing, and then we have horizontal tangent as well, then it's an inflection point too. In summary, we're going to have something like this. The original function is concave up. First derivative is increasing. Second derivative is positive. These three are more or less the same. Yes, there are some counterexamples here and there, but those are really, really, really rare. And you have to create some special case that derivatives, so first derivative, second derivative, do not exist or something like that. So those are really rare. So you can just assume those are more or less equivalent, at least in 1000 level. Now, original function is concave down. The derivative is decreasing, and second derivative is negative. Those are all more or less the same. Inflection point, that's when the concavity changes. First derivative function changed from increasing to decreasing. That's going to be local maximum. Or decreasing to increasing. That's going to be local minimum. In that case, of course, the derivative of derivative is going to be the critical point of the first derivative, so it should be 0. Inflection point is 0. Inflection point means the second derivative is 0, but not always vice versa, because second derivative is 0 does not always mean the concavity changes, because it doesn't always say the first derivative has local maximum or local minimum. It can be neither. So it can be a little bit tricky to tell the truth. So we have something like this. Inflection point, that's equivalent to f has an inflection point, that's equivalent to f prime has a local maximum or local minimum. So these two equivalent, that's true. But the second derivative is 0. This one is not equivalent. As a matter of fact, it's only this way. So there is an example, the second derivative is 0, yet first derivative is not a local extremum, neither maximum nor minimum. Consequently, the original function is not an inflection point. So this one here, we have equivalence. This one here is not an equivalence. So be a little bit careful about this, even though, oh boy, I admit it's unlikely that I'll pick up this kind of problem in the exam and virtually kill off everybody. If I do, then it's gonna be a small portion of the problem. So you see, in 10-point problem, most people score 8 out of 10 okay, but the other 2 points is for A students, kind of like that. It's really tricky point, but still, they are not completely equivalent. Okay, all right. So much for section 1. Let's discuss actual problems in separate videos.